Hello friends, I welcome you in lecture number 30 on partial derivatives. In this lecture, we will discuss one more problem on method of Lagrange multipliers. This question was asked in GTU Winter 2019 exam. We understand this question. A rectangular box open at the top is to have a volume of 108 cubic centimeter. Find the dimensions of the box requiring least material for its construction. So here we have to construct a rectangular box which is open at the top and having volume 108 cubic centimeter in such a way that least material is required for its construction. So we have this type of situation. Suppose I consider this rectangular box and it is open at the top. Suppose x is the length, y is the width and z is the height of the rectangular box. We have to construct this rectangular box in such a way that volume is 108 cubic centimeter and we have to find out values of x, y, z for which least material is required to construct this rectangular box. So the amount of material required will be equal to surface area of this box, and we know that surface area of the box which is open at the top is given by x into y plus 2yz plus 2zx. We have discussed how this is coming in lecture number 29. So if you have not seen lecture number 29, I suggest you to watch lecture number 29 first and then go for this lecture. So again here we have to construct a rectangular box whose volume is 108 cubic centimeter such that least material is required for the construction of this box. That means we have to consider the dimensions of this box in such a way that volume is 108 and surface area is minimum. We have to minimize surface area subject to this condition that volume is 108. So we have to write in this way: let x, y and z be the length, width and height of the rectangular box as shown in this figure. Then the volume V of the box is given by V equal to x into y into z. Since the box is open at the top, its surface area is S equal to x into y plus 2yz plus 2zx. We have to construct a box of volume 108 cubic centimeter such that the least material is required for its construction, or we have to construct a box with minimum surface area. In other words, we have to find values of x, y, z satisfying this constraint. Volume is 8 and volume is given by x, y, z, and in such a way that we obtain minimum surface area, or this we can say in other words, the problem is to minimize this surface area subject to the constraint x, y, z equal to 108. So the function which we want to minimize is this function s of x, y, z, and this is the constraint. We consider function g x, y, z equal to x, y, z minus 108, and we solve the system. Gradient of s equal to lambda times gradient of g together with this constant 1. Now we simplify this. Gradient of s equal to lambda times gradient of g. This implies gradient of s is del s by del x, del s by del y, del s by del z equal to lambda times gradient of g, that is lambda times partial derivative of g with respect to x, derivatives of g with respect to y and z, and then we multiply each component by lambda, and we have these two vectors which are equal. Therefore del s by del x is lambda times del g by del x, del s by del y equal to lambda times del g by del y, and del s by del z equal to lambda times del g by del z. Now we first find out partial derivatives of s with respect to x, y, z. Del s by del x will be equal to derivative of xy with respect to x is y, this is 0 plus 2z. Then del s by del y is derivative of xy with respect to x is x, with respect to y is x, plus derivative of 2yz with respect to y is 2z, and the derivative of this term is 0. Del s by del z is 2y plus 2x, and the derivatives of g will be del g by del x equal to derivative of xyz with respect to x is y into z, del g by del y is x into z, and del g by del z is x into y. We substitute all these derivatives in these three equations and we obtain these equations number 2, 3 and 4. Now in equation 2, in the right hand side x is missing, here y is missing, here z is missing. So we can multiply this equation 2 by x, this by y and this by z, so that right hand side of these equations will be same. So in the next step we multiply 2 by x, 3 by y and 4 by z, and we obtain x into y plus 2xz equal to lambda xyz. This is multiplied by y, that is x into y plus 2yz equal to lambda times xyz. This is multiplied by z, so we have 2yz plus 2zx equal to lambda times xyz. Now we are having right hand side same in all these three equations, so we can compare equations 5 and 6 or 6 and 7. Suppose we compare equations 5 and 6, then because right hand sides are equal, we must have xy plus 2zx equal to xy plus 2zy. So that we have written here. Now we consider this on left hand side, and xy will cancel out, and 2zx minus 2zy equal to 0. Here 2z is common, that we can take outside, and we have 2z times x minus y equal to 0, and 2 is always non-zero, therefore z is 0 or x minus y is 0 or x equal to y. If z equal to 0, then if we see what is equation 1 is xyz equal to 8. If z is 0, then we obtain 0 equal to 108, which is not possible, so z cannot be 0. Or we know that xyz are dimensions of the box, so they are always positive. So in that way also we can say that z equal to 0 is not possible. Therefore we obtain this x equal to y by using equations 5 and 6. Now we compare equations 6 and 7. Right hand sides are same. Therefore xy plus 2zy and 2yz plus 2xz are equal. By comparing 6 and 7, we obtain xy plus 2yz equal to 2yz plus 2xz. 2yz will cancel out. If we transfer on this side, we will have 2yz minus 2yz, that is 0, and we are left with xy minus 2xz equal to 0. We can take x common, and in the bracket we have y minus 2z equal to 0. Therefore x is 0, y equal to 2z. X equal to 0 is not possible. Again it will violate the condition 1, which is xyz equal to 108. If we take x equal to 0, we obtain 0 equal to 108, which is not possible. Or we can say that x equal to 0 is the length of the box, and we consider it as always positive. Therefore x is non-zero, and we obtain y equal to 2z. So after comparing these right hand sides of equations 5, 6 and 7, we obtain that x is equal to y and y equal to 2z. That means we obtain x equal to y equal to 2z. Now we use equation 1. Equation 1 is x, y, z equal to 108. So here we replace x by 2z, y by 2z, and we keep z as it is, and we obtain this. Now this is going to be 2 into 2, 4, and we have z into z into z 3 times, that is 4z cube equal to 108, and therefore z cube equal to 27. From this we can write z cube equal to 108 divided by 4, that is 27, and therefore z equal to 3 or minus 3, but we consider dimension of the box as positive, z being the height of the box. Therefore z is 3, and x is equal to 2z, and z is 3, therefore x is 6, and x and y are equal, therefore y is also 6. Therefore the dimensions of the box are x equal to 6, y equal to 6, z equal to 3, and we can see these dimensions satisfy the given constraint. If we multiply x, y and z, we can see that we have 6 into 18, that is 108. So we obtain these values of x, y, z for which s can be minimum. So we find out surface area at this point. Surface area is x into y plus 2yz plus 2zx. We put x equal to 6, y equal to 6, y equal to 6, z equal to 3, z equal to 3, x equal to 6. And after doing all these calculations, we obtain that surface area at point 663 is 108, and this must be minimum. The point which we have obtained using Lagrange method, at that point surface area is minimum, and that we can verify by considering another point different from this point satisfying this constraint and finding value of surface area at that point. So if we consider any other point satisfying this constraint, then surface area at that point must be bigger than 108, which is the surface area at this point. Now how to select the point satisfying this condition? So we can write z equal to 8 divided by x into y. We consider x and y positive because they are the dimensions of the box. So we can select arbitrary value for x and y, and we will obtain value of z. So in that way we can find out the another set of points. So that we have written here. Now we find another set of values of x, y, z satisfying the constraint x, y, z equal to 108. For that we rewrite this as z equal to 108 by x into y, and this is because x and y are dimensions of the box, therefore they are positive. Suppose we take x equal to 2 and y equal to 3, then z will be 108 divided by 2 into 3, that is 6. So we obtain z equal to 18. So the point 2, 3, 18 satisfies this condition. We can see it is 2 into 3, 6 into 18 is 108. Now we calculate surface area for these values of x, y, z. So we have x into y, that is 2 into 3, plus 2 into yz, that is 2 into 3 into 18, and 2 into zx, that is 2 into 18 into 2. And we obtain that surface area at this point 2, 3, 18, which satisfies this constraint, is 186, and this is bigger than surface area at this point 663, which we have obtained using Lagrange method. So this point was arbitrarily selected satisfying this constraint, and we obtain that surface area at this point is bigger than surface area at this point 663. So we can say that surface area is minimum at point 663, or we can say that the dimensions of the box requiring least material for its construction are x equal to 6, y equal to 6 and z equal to 3. So in this problem, volume is given, or we have constraint in terms of volume, and we are minimizing the surface area. In lecture number 29, we had given the surface area. Our constraint was on the surface area, and we find out the volume or maximum value of volume. So you can compare both the problems. In both the problems we are applying Lagrange method. The problem which we have done in lecture number 29, in that problem we are maximizing the volume, and in this problem we are minimizing the surface area. So that is the difference between these two problems. So this is all about this session. I hope you like it. Thank you.